Okay, so condensed structures are really great for conveying structural information in one line, which is very useful. So for example, like websites will tend to use them a lot. So there's something important, they are something that is important to know, but the real sort of way that we're going to be doing it just over and over and over again is through what are called bond line structures. These are these drawings that are probably most associated with organic chemistry, the hexagons, right? Yeah, so these are just great ways of conveying structural information. And so just to sort of set it up as to why here, this is a classic organic chemistry molecule, amoxicillin, which is an antibiotic. You can see this is the Lewis structure for amoxicillin. It's really complicated to see all of the different features that are going on here. You sort of have to hunt through to be able to find, for example, the carbons that are double bonded with oxygens or OH groups, etc. So then here we have the bond line structure for that same molecule. And you can see that it's a lot cleaner, so it's just a lot easier on the eyes to look at. It conveys all the same information though. So that's going to be the point of today, is figuring out how to jump from one to the other and understand what that information is. And you can see that the more important structural features, again, see I even missed one, carbons double bonded to oxygens, are sort of easier to point out. Okay, so that's what we're going to be building towards. So let's start sort of step by step here. So these are structures that have this sort of zigzag associated with them. All right, what the heck is the zigzag? Well, the important thing here, again, we're talking about organic molecules. So there are carbons and hydrogens that are being implicitly represented in these drawings. So let's start with the carbons. The carbons are going to be located at endpoints and intersections in your bond line structure. Every endpoint and intersection will have a carbon atom associated with it. So counting carbons in here, we have 1, 2, 3, 4, 5, 6. You're going to hear me talk about counting carbons a lot. Something that you should sort of get good at. It's a really good way to proof your work and make sure you're not making a mistake. But yeah, so something you're going to hear me say a lot. So again, when we have our sort of zigzags here, endpoints and intersections, that's what you want to have sort of ingrained in your mind. So everybody pause and take a second and figure out where the carbon atoms are located in the structures below. All right, so endpoints and intersections. I think this is actually the exact same example. Okay, endpoints as well as intersections. And look, here we even have a different one here. This is now going to be a carbon that's bound to 3 other carbons, not just 2. Again, same situation here. These are intersections, and then we have our endpoints. So all 3 of these are compounds that have 6 carbons. And I'll just note that these are also single bonds, right? They represent carbons that are bound to one another with just a single bond, so 2 electrons being shared. If we wanted to represent double or triple bonds, we do that with multiple lines. Still, considering that carbons are at endpoints and intersections, right? So again, here's my intersection, and here's my endpoint. You see one bond we have kind of like floating above the other one. And with the triple bonds, same sort of idea. These are actually kind of the weirdest. They trip people up the most because every time you see a triple bond, you have to remember that on the end of that is a carbon. Sometimes there isn't this little gap like there was in this drawing here. It's just a straight line, right? So this also has 4 carbons, endpoints and intersections. And just note that these are intersections. Okay. Triple bonds, we make sure to draw in a straight line, right? So this is the correct way to draw a triple bond. You would not see it in a zigzag. Why would that be? Hopefully you remember that these compounds here are linear. These triple bonds here are linear because these carbons on either end have to be sp hybridized. Okay. So those were the carbons, right? So let's take another example down here just to make sure we're extra great at this. We have all of our endpoints, and look at what a double bond endpoint looks like. So there's a carbon there, oh, and an intersection here, can't miss that. All right. So 6 carbons here. But if I'm going to focus on this carbon right here, for example, it's bound to 2 other carbons in my drawing. Well, it can't be done then, right? The drawing can't be complete because carbon can't just have 2 bonds. So what the heck is going on there? Well, that's how the implied hydrogen position information comes into play. You always just complete the number of, the octet rather, of the carbon atom with hydrogens. So focusing on this carbon here, that would have 2. Likewise, this other carbon, that would have 2. What about this terminal carbon? How many is that going to need? Right? Each one of those terminal carbons are going to need 3 hydrogens to complete their octet. And what about my double bonded carbon up at the top here? That also, oh, not carbon. That also is going to need 2. Okay, so the position of the hydrogens is implied in these bond line structures as well, carbons and hydrogens. So everybody take a second, remember the zigzag sort of deal, and see if you can't tell me what the bond line structure for this simple compound is here. Again, one of the things that I'm going to do is count carbons. I'm going to go 1, 2, 3, 4. Okay, great. 1, 2, 3, 4. And then honestly, I'm also always going to go back 1, 2, 3, 4 and double check. If this was in the classroom, you'd see me tap the board all the time as I go through and count carbons on molecules after I draw them, because it's super duper easy to accidentally just lay down an initial, accidentally lay down another line. Often the initial carbon gets forgotten sometimes. Now, remember this Vesper theory, these bonds want to be as far apart as possible, so we draw them as such. When we have 3 bonds, for example, you will always see it in that kind of trigonal planar drawing as opposed to this drawing here. You should never have acute angles in your bond line structure. If you do have, for example, carbon that's bound to three methyl groups, that structure would be drawn like this. So then, because you do have 4 bonds that you explicitly have to draw in there, you would represent them with a 90-degree angle as opposed to down here. This is more like a 120-degree angle. But nonetheless, you would never have an acute angle in your bond line structures. So we try to keep them as close to what the actual kind of geometry of the molecule would look like. I mean, again, it doesn't work perfectly, but yeah, that's the idea. Remember that single bonds rotate. This is a normal sort of bond line structure to look at. This one is not so much, only because our convention is to go left to right like we read. They're actually the exact same structure. And that's something to remember not only when we're talking about drawing bond line structures, but also just when we're talking about chemistry, is that everything is rotating about its single bonds quite a bit. So yeah, just something to keep in mind. But anyways, these are 2 equivalent bond line structures for the same molecule. All right, and the last rule would be like your heteroatoms or anything other than carbon and hydrogen. And I guess this is a key word that gets thrown around a little bit. That's good to know. I'm talking about anything other than carbon and hydrogen. That's going to be explicitly written. And not only is it going to be explicitly written, any hydrogens associated with it are also going to be explicitly written. So this is the Lewis structure that corresponds to this bond line structure over here. And notice how not only is the oxygen written, but also that hydrogen is explicitly written in there as well. Actually, take a second and count carbons and hydrogens in this whole compound. See if you can't give me the molecular formula for it. Okay, so 1, 2, 3, 4. I'm going to have, of course, I could look over here, but that would be cheating. So let's just go here. Each of these have to have 2. Each of these have to have 3. And don't forget this guy here only has 3 bonds, so it has to be put in. Those carbons at the middle of a 3-carbon intersection or a 2-carbon heteroatom, something like this, where they're in the middle of 3 lines, those get missed a lot. They hydrogens on them, rather. So something to keep track of. All right, so then if I'm going to just total this up in terms of getting my molecular formula, because that's what I asked, it would be C4. We have 6, 7, 8, 9, 10. And oxygen. And then, of course, remember rules for connectivity. Carbon's never going to have more than 4 bonds. Unless there are formal charges, you won't see more than 3 bonds for oxygen, or I'm sorry, more than 2 bonds for oxygen, or 3 bonds for nitrogen, etc. And we'll talk about formal charges this week as well, so that those situations, when they are allowed to arise, you'll sort of know. Okay, so now just a little bit more practice. Everybody take a second and pause the video and go through these problems, and then play the video back and I'll go through them and you can make sure you got it down. Okay, so again, molecular formula, but really what I am curious about is, can you find number of hydrogens and carbons? So 1, 2, 3, 4. And then we're gonna put in our hydrogens terminal. Those methyl groups, they have to have CH3. If they're in the middle, CH2. Okay. Now we have a hexagon, right? What were we talking about? One of the things to remember in these cyclic compounds here, actually, let's just mark it on here first. Is again the number of hydrogens. You're going to have 2 on each of these corners. We have our methyl groups here, these terminal carbons. Okay, and then got to remember that these also need a complete octet. So 1, 2, 3, 4, 5, 6, 7, 8 carbons, C8. (16 hydrogens). Cool. All right. So now going from Lewis structure to the bond line structure. Again, one of the things I'm going to do first is count carbons. And my goal is going to be actually to find the longest chain through this molecule that I can. So in this case, 1, 2, 3, 4, 5, 6, 7 is the longest contiguous set of carbons that I can get, right? So not counting all carbons, just the ones that I can connect in the longest way. So again, 1, 2, 3, 4, 5, 6, 7, is that what I said? Yeah. So 2, 3, 4, 5, 6, 7. Okay. And then I also like to double check, or as a way to double check, to count carbons here as well, where I sort of 1, 2. Okay, I should have a methyl group off of carbon 2. So 1, 2, 3, 4, 3, 4. Notice that even though this group here was drawn up, I could include it in my contiguous line, my longest line. So it already was drawn. Okay. So here we have one of those carbons that actually has 4 carbon-carbon bonds, so it's going to have to be drawn as that intersection there. But now I can start zigzagging. Okay, so I have already drawn one of the, again, sort of keeping track of what's what. This carbon here has already been represented. That's this carbon there. So the next thing that needs to happen is an oxygen, followed by another carbon, followed by 1, 2, 3 carbons, let's say. So 1, 2, 3. And carbon 1, 2 in that line has an OH group off of it. All right, now this one has some double bonds in there. Notice no matter how it's drawn in the Lewis structure, that's not how it would be on the bond line. We're going to need that zigzag. And then we should have 1, 2, 3, 4 carbons. So I've drawn 1, 2, 3, 4. And this last one, let's see what this group looks like here. Double bonded oxygen, a single bonded OH group. Okay, so make sure you practice these. These are going to be a huge part of our organic chemistry life this semester. And once we get these skills down, we'll be able to start talking about chemical reactions of these molecules. But right now, all we're really focused on is being able to represent them correctly. Okay?